Imagine a world where AI doesn't just predict the next word, but understands the structure of thought itself. Not just mimicking language, but reasoning, planning, and solving problems like a human. That's not science fiction. It's the frontier of modern AI, reasoning models that go beyond pattern matching and into true cognitive behavior. For years, large language models have dazzled us with their ability to write poetry, answer questions, even debug code. But here's the catch: they're not really thinking. They're statistically predicting sequences, like a supercharged autocomplete with a PhD. They don't understand the meaning behind the words. They just know what comes next. But what if we could build models that don't just generate text, but reason through problems step by step? That's where reasoning models come in. And the breakthrough isn't just in architecture, it's in process. Let's dive into the mechanics of how these models actually work, and why they represent a quantum leap in artificial intelligence. At the heart of this shift is a concept called chain of thought, COT, prompting. Instead of asking a model, what's 25% of 80, and getting 20, we say, let's think step by step. And the model responds, 25% is the same as 1/4. 80 divided by 4 is 20. So the answer is 20. This tiny shift in instruction unlocks a massive leap in performance. Why? Because the model is now forced to simulate a reasoning process. It's not just outputting a result, it's generating an internal reasoning trace, a sequence of logical steps that lead to the answer. But COT prompting is just the beginning. The real game changer came with self-consistency and tree of thought, TT, reasoning. Self-consistency takes COT further. Instead of generating one chain of thought, the model generates multiple reasoning paths. Then it evaluates which path leads to the most consistent answer. This is like having a team of AI thinkers debate different approaches, and the best one wins. But tree of thought takes it even deeper. Imagine the model doesn't just follow a single linear path, but explores multiple branches, like a tree. At each node, it considers different possibilities. Should I try solving this algebra problem by substitution or elimination? It explores both, evaluates the outcomes, and prunes the less promising branches. This is where we start seeing models tackle complex multi-step problems, like planning a route through a maze, solving advanced math proofs, or even writing coherent, structured essays with internal logic. Now here's where it gets really technical. The key innovation behind these models isn't just in how they're prompted, it's in how they're trained. Traditional LLMs are trained on massive text corpora using next token prediction. Given a sequence of words, predict the most likely next word. This is great for fluency, but terrible for reasoning. But reasoning models are trained using reasoning-specific objectives. One such method is reinforcement learning from human feedback, RLHF, but not just for alignment. Here, the reward function is designed to value correct reasoning paths, not just correct answers. For example, if a model correctly solves a math problem but uses a flawed logical step, like dividing by 0, it gets penalized, even if the final answer is right. This teaches the model to value correctness of process, not just correctness of output. Another powerful technique is self-training with feedback. The model generates its own reasoning chains, evaluates them against known correct solutions, and uses that feedback to refine its internal reasoning patterns. It's like an AI tutor that grades its own homework and learns from its mistakes. Now let's talk about neural-symbolic integration, a frontier that's quietly revolutionizing reasoning. Traditional neural networks are great at pattern recognition, but weak at symbolic logic. Symbolic AI, on the other hand, excels at formal reasoning but struggles with ambiguity. The fusion of the two, neural-symbolic systems, creates models that can both understand language and reason with logic. For instance, a model might use neural components to parse a natural language question, then pass that understanding to a symbolic engine that applies formal rules, like a logic solver or a theorem prover, to derive the answer. This hybrid architecture is what powers systems like Neuro-Symbolic Concept Learner, NSCL, and DeepMind's AlphaGeometry, which solved geometry problems at the level of human Olympiad participants, by combining deep learning with deductive reasoning. And the most exciting part, these models are becoming increasingly transparent. We're seeing the rise of explainable AI, XAI, techniques that allow us to trace the reasoning steps of a model. We can now see why a model chose a particular path, what assumptions it made, and where it might have gone wrong. This isn't just about trust, it's about debugging, verification, and real-world deployment. But we're not there yet. Challenges remain. Reasoning models are still computationally expensive. Generating multiple reasoning paths, evaluating them, and pruning inefficient ones requires massive compute. They're also prone to hallucination, especially when exploring deep trees of thought. A single wrong assumption can cascade through the entire chain. And while they're better at logic, they still struggle with common sense, real-world context, and long-term planning. They don't understand the world, they simulate reasoning about it. So where does this leave us? We're standing at the edge of a new era in AI, not one where machines just generate text, but where they think. They don't just know what to say, they know how to think. This isn't about replacing human intelligence. It's about augmenting it. Imagine a researcher using a reasoning AI to explore hypotheses, a doctor using it to diagnose complex conditions with full transparency, or a student learning problem-solving by watching an AI break down a difficult math problem step by step. The future isn't just smarter models, it's more thoughtful models. And the most powerful insight: the best reasoning isn't just about having more data or bigger models. It's about teaching the AI to think like a human, to reason, to question, to explore, and to learn from its mistakes. Because in the end, the goal isn't to build machines that mimic human thought. It's to build machines that help us understand it better. This is the frontier of AI. Not just language, not just prediction, but reason. And it's just beginning.